Hello and welcome to the lecture of linear algebra. Today we'll talk about the application of linear algebra, and one of the very famous application of linear algebra is Markov chains. This topic is continuation of the previously discussed topic, where we talked about the application of linear algebra to different equations. So if you remember from first few lectures that we covered in this course, we talked about one of a very good example about the population migration within urban and rural areas, and we were actually what we were doing was that we were giving the year-wise population growth in urban and rural areas. So given there's a certain amount of people that are coming into the urban area, and there are a certain amount of people that are going out of the urban area. Similarly, there are certain people that were moving back to the rural area, and some of the people that were moving from the rural area to the urban area. So we remember this, that say, so if there's a vector which is, if you remember, that is 0.60 and 0.40, that would indicate that 60% of the population lived in the city or the urban area, and 40% of the population living in the rural area. Okay. Now the thing here is Markov chains have been used to study these kind of models, where is a certain kind of probability associated of in any process. For example, in this process, a certain probability associated with of the people that are moving out of the city, or a certain amount of people that are living in the city, and similarly certain amount of people living in the rural city, and so there are probabilities associated with this, that some of the people might come into the rural area and some of the people might leave the rural area. So Markov chain has been applied in a lot of different areas of engineering. It has been applied in communications. It has been applied in control. It has been applied in businesses. So one of the very famous process that can model through Markov chain is a queuing process. So for example, if you are going to a big store, for example such as Metro, so how much counters they will be opening at a particular time is dependent on how many people are coming into the store and how many people are going out of the store. Of course, I mean, when you observe this going in and out of the people over a long term, you will find the probabilities associated with this incoming and outgoing of the people, and then you can decide based on that probabilistic model that how much counters a metro can open at a certain time, or say how much on average counters could be opened by a metro, in a day or in a week or say in a month, right? So we generally say when we talk about Markov chains, we talk about a probability vector. And this so in generally we say this as a probability vector which actually adds up equals to 1. Markov chain is a series of probability vectors, say x naught, x1, x2, uh, such that, so if you want to uh, if you were in some initial state, say for example in this case 60% of the population was in city and 40% was the population in rural areas, after so given a certain transition matrix, this is called a transition matrix, normally referred as probability transition matrix. Say I gave you a question in this exam as well, where you were finding what is the average population after 2 years. So what you were doing, you were actually building up a transition matrix, say, and then you were saying that x of 1 is equals to some matrix x naught, and then you were saying that x2 is sometimes x1. So this was a transition matrix. But when we talk about, when we model the process in terms of probabilities, we don't talk about transition matrix, we talk about a probability transition matrix. So the next state, the evolution of next state is dependent upon this probability. So it means, as an example I gave you, for example the metro, you can think of this probability matrix as modeling the number of people, what is the probability of number of people going into the metro and at a certain time, and the probability of people being served or coming out of the metro, right? So this actually defines the rate or the probabilities at which these customers can be going in or out of the system. But if you look at long-term thing here, it means x2 can becomes p times x1, and x3 can becomes p times x2, and similarly if I want to generalize this can become x of k plus 1 is equals to p times x of k. What it means to say that evolution of the next state is dependent upon this probability transmission matrix P, right? This is x of k is normally referred as a state vector. So if I read it by all these definitions, right, given a state vector, you can move to another state, right? So with a certain amount of, with a certain multiplying with a certain matrix P, which is a probability transition matrix. So to give you an example on that, say for example at a certain amount of time there were 10 people in a metro supermarket, right? What is the probability after, let's say, 10 minutes you will have you will have a certain amount of people? You can find it by multiplying this as, think of this as x plus 1 is equals to p times 10. Okay, so this is how, because in that amount of time some of the people will be coming in and some of the people will be going out, right? On average, what would be the next state after some certain amount of time, or what will be the number of customers in the metro after a certain amount of time? You can find it through this probability transition matrix. Now coming back to the example that we covered, or I gave you in that paper as well, if you remember that this was the matrix that we were dealing with, which was, if you were looking at the city, 0.95, it was suburbs, or you say rural population, which is 0.03, and this is 0.05, and it was 0.97, and this was city, and this was suburbs, right? It was from, and it was actually to. These two are from to. So So how many people from city remain in the city is 0.95. How many people from suburbs will move to city is 0.03. And similarly, how many people from city will move to uh, the suburbs is 0.05. And how many people from city from suburbs will actually move to the suburbs, from city to suburbs, and from suburbs to suburbs you will have 97. So you can see here along this axis here, the sum of the probability, if you add them up, is equals to 1. If you add them up here, that will equals to 1. Okay, so this is actually a probability transition matrix. Okay, now so this is M could be defining as a migration matrix. So what it's saying is that 5%, or the probability 0.05, the city population is moving to the suburbs, and actually the probability of 3%, or let's say 0.03, the number of people from suburbs are actually moving to the city, right? So suppose that in a certain year there's a population of, let's say, 6 lakh, and there is a certain population in the city, and 400,000 is the population in the suburbs, right? So so what will be the population in city and suburb after 1 year? So you can think of this as x naught, and then you can say here x is 1 is nothing but m times x naught, right? And if you multiply them up, right, so that would be 0.95, 0.05, 0.03, 0.97. You will end up here as 600,000, 400,000, right? And when you multiply both of them up, right, you will eventually get to 582,000 and 418,000, right? Now similarly, after 2 years, what I'll do is basically x2 times, and again, because the statistics or the probabilities will remain the same over the year, that's the main assumption. So it means x2 is m times x1. So this transition will not change, this transition matrix will not change. So over the years this will remain the same, but what we can do is now actually find the next year population in city and suburbs, right? And you can keep moving on and on and on. And so that could be something like this. So x2 again can be as, if you multiply this up, you will have a term which is 565,000 and 435,000, right? Similarly, you can keep multiplying and you can keep finding the population of the city and suburb in subsequent years, right? So this is a state vector. This is a state vector. So you can find the next state by simply multiplying this transition matrix M with the one in the previous state. So next state can be found by multiplying the probability transition matrix with the current state, which is x1. Okay. So how this is the evolution of this is the basic concept of Markov chain. So it means you define the set of states and you define the probability transitions between them, and then you can work out the different parameters or different states depending upon this transition matrix. Now now suppose, say for example, so in an election, say in in Pakistan, right? There is a certain state which is their election is held, and what we are doing here is we are saying that how many people will vote for let's say PMLN, how many people will vote for PTI, and how many people will vote for say PPP, right? Now the thing is, if we look from election to elections, right, so if we look at a lot of elections, then we can work out the probabilities that a certain in a certain city, or in a certain province, or in a certain, even in a certain district, how many what is the probability that that people in that city or a suburb will keep on voting for PMLN, keep on voting for PTI, and keep on voting for PPP. Similarly, if you look at those elections, you can work out how many previously voted for PML will now going to vote for PPP, or how many previously in PTI are going to now vote for PPP. So it means you can think of this as P as again from, so this will become PMLN, this will become PTI, this will become PPP, and again 2 here, which is PMLN, this PPP, PTI, and PPP, right? So you can work out this this situation, and of course this can all be worked out if you have lot of observations to continue with. It means you have able to find you are able to get the numbers which can help you build that matrix. Okay, so in that case, if I write this 0.70, say for example, it means 70% of the population that previously voted for PMLN will vote for PMLN, right? Now similarly, how much population that voted for PTI will keep on continuing vote for PTI is 0.80. Of course, these numbers have came from lot of observations. It means you have seen a lot of elections, and that number is coming from that. So you go on in the population, you take surveys, and then you work out those probabilities. And again, how many people voted for PPP will keep continuing or vote for PPP is, let's say, is 0.4. Okay. Similarly, of course, people will switch their preferences, and of course, let's say 70. There are a certain amount of people that switch their preferences from PMLN to say to PTI, or sorry, from PTI to PMLN. In this case, this will be 0.10, and from PPP, some people actually voted to PMLN, which is now 0.30. Okay, and again, similarly, I can work out that how many people from PMLN will switch to PTI. It will be 0.20, and similarly, you can say all that. You can write those numbers, and then you can interpret those numbers. Now, again, if you can see here, this will sum up to 1, this will sum up to 1, this will sum up to 1, and this is a very fundamental concept in probability. That all the probabilities should add up equals to, in a sample space, should add up equals to 1. Now you can actually make a diagram out of it, right? And this diagram can look like this, right? So it means you can say PMLN, and then you can say PTI, and then you can write PPP, right? It means people voting for PML1 will keep on continue voting for PMLN. So you can write this, and arrow indicate that it will be 0.7. Okay, and some of the people from PMLN will now going to vote for PTI, which will be 0.20. So the arrow indicates the direction here is 0.20. And again, some of the people from PMLN are going to vote for PPP, that will be 0.20. 0.10. Again, the arrow indicates the direction in which the switch is going to happen, 0.10. And again, then you can say you can write the way around, which is 0.10. So 0.10 is from PTI to PMLN. So PTI to PMLN is actually 0.10. Okay, and again I can say how many people from PTI will keep continuing voting for PTI, which is this number here, which is 0.80. So you get here again rounding it off and 0.0. And again, when you say how many people will now from PTI will vote to PPP, PTI to PPP is actually 0.10, which is that number here. And again, if we go from PPP to PMLN, so it means PPP to PMLN here will actually be 0.30 from direction again. Please check the direction of the arrow, and from PPP to PTI will be 0.30, and only 40% of the population which previously voted PTI will keep continuing voting for PTI, which will be PPP, which will be 0.40. Now, okay. Now we have defined the probability transition matrix, and we have defined what we call is a state transition diagram. This is called a state transition diagram. Yeah. So you can think of another example as well. Say for example, let's say in a metro, say, so you can think of this as number of people as a state. So you can think of as there is no customer in the state, right? There will be another customer. A customer will come with a certain probability, right? It is, let's say, P0, and of course it will go out with a certain probability. Let's call this as P1. Okay, let's indicate 0 to 1 and 1 to 0. So this is going from 1 to 0. So if there is no customer in a certain time, at a certain time, the probability that a new customer will come is probability 0, 1. It will go from 0 to 1. And then if there was initially a customer in the metro, it will be served and it will be leaving the metro, indicating that there will be no customer in the metro. So for example, there is only one possible customer allowed in the metro, and there is a possibility that in that time duration no customer will come, and the probability of that is P00 again, right? Similarly, there is a probability that a certain customer will remain in metro, is a probability P11. So you can now think of a state transition matrix P as nothing but equals to S00 as P00, and again from P01, and you can say as P10, we say P11. Okay. Now similarly, you can develop more complex models based on Markov change, right? Now the thing here is, say, coming to that previous example of the election scenario, assume that we have a demographic that initially voted for something like this, which was, it means 55% of the population actually voted for PMLN, 40% of the population which voted for PTI, and 5% of the population which voted for PPP. What I want to see is what is the probability that I will have, what is the voting percentage, the voting probabilities in the next election, which is again here 0.55, 0.40 and 0.05, and this P matrix will remain the same, okay, the one that we discussed earlier. Again, now this is P times x0. Again, I can write this as x2 as p times x of 1. The one you calculate here will be substituted here, and then you can find x2. And actually you can keep going that. I mean, the book already has a solution, so I don't need to calculate that. It comes out 0.440, 0.445 and 0.115. Okay, and again when you do that, it comes out to be 0.3870, 0.4785 and 0.1345. Okay, now this is actually what we call, you can think of this as predicting. I mean, you're saying that what is going to be the state after an election, right? Given that you have a probability transition matrix and you know the initial state, you can actually predict on keep on predicting the next state and state and set. So actually what you're doing is actually predicting the future in a sense, right? So let's say we have a matrix here P, which is the probability transition matrix 0.3 and 0.2. This is 0.2, 0.8, 0, 0.3, 0.4 and 0.4, and some initial state x0 is given as 1, 0, 0. Okay, so these are, we are saying they are coming from some Markov process or from Markov chain. We can say then x1 is equals to px0, which comes out to be 0.5, 0.3, 0.2, right? Now if I calculate x2, which is p times x1, I'll get here is 0.37, 0.45 and 0.18, right? Similarly, you can go x3, which is p times x2, comes out to be 0.329, 0.525 and 0.146, right? And similarly, if you apply keep on doing for, let's say, x14, you will come out as 0.30001, 0.5996 and 0.10002. And if I do for x15, you come out again very similar, which is 0.3001, 0.5998 and 0.10001. So you can see here that after certain amount of iterations, you hardly see any difference between the subsequent states. Hardly any difference. It means, it seems they are converging to something, right? So I mean, it means you can think of this x14, you can think of this now as x15 is nothing but equals to p times x14. x14, there is no difference between x15 and x14 numerically, if you look from numerical precision point of view. So it means you can think of this as q and this as p and this as q. It means if I designate a vector q, x14 as q, it means after an iteration the resultant vector is also very close to q, right? This is called actually the equilibrium condition or the stationary condition, or is even often said that this is a steady state vector. This is a steady state vector. It means, given this probability transition matrix, after a certain amount of transitions, this will not change. This will not change, and that's why it's called a steady state vector. That's why we call it a steady state vector. So now, if you look at, if you remember the example that I gave you about the metro earlier, right? So it means that if the customers are going in and out of the system, right, with a certain amount of probability which doesn't change over the time, it means starting from any initial position, right? Starting from any initial position or any number of customers, right? We can actually find out that on average or in a steady state condition, how many customers will be there in a metro supermarket, right? Provided that this probability transition matrix remains the same. So So how this is how the actually big companies, big superstores, or stores like or malls like Centaurus, or the big malls like High Point in Australia, or even in New York City, they try to work out these probabilities, and they try to look for the steady state vectors to design the systems. Similarly, you can do for in communication systems. Say, for example, if you're talking about a network in which packets are coming in and of course being transmitted, right, and coming from different sources, so you know what is the probability that the packet will come and what is the probability that packet will be transmitted. So you can work out on average how many packets will be there in the system. So if you're designing a PaaS network, right, so it means you will now understand, say for example a small scale PaaS network, you will now understand that how many users are there, how many on average, how many packets they will generate, and how many packets they will be transmitting, the probability they will be transmitting, right? So you can work out the capacity of the system that is needed to run a decent sized PaaS system, right? So this is actually achievable through Markov chain, right? And one of the very good problem is to find those probability transition metrics, right, which can only be found by observing the system for a long time, right? So it means you cannot, but we are not actually concerned about this how they could be found, but just to give you a hint, this actually can be calculated by observing a lot of values, right? So but once these values are calculated, you can actually find a steady state vector in which that you will find a state that will not change, right? It will remain in that state after certain amount of transitions, right? So similarly, if you again coming back to the example that we talked about about the migration of the population, you can work out that there could be a scenario in which M is the migration matrix and M of Q is equals to Q, right? So it means what it's trying to say here is that you find the steady state vector Q, when you multiply with M, it will remain as Q, right? So it means there is no more change in the population of the city or the suburb, right? So if let's say we've been asked to find that steady state vector given a certain migration matrix or a probability matrix, a probability transition matrix, let's say P is that matrix, which is 0.6 and 0.3 is 0.4 and 0.7. We've been asked to find the steady state vector for this for the system defined by this probability transition matrix. Now in this case, that will be again coming back here, we know that PQ will be equals to Q, and you can think of that as nothing but PQ minus Q equals to 0, which in turn can be written as P minus PQ minus Q times I. I, as you know, is nothing but a identity matrix, and when you multiply any vector by identity matrix, it will come as again as the same vector. So keeping the order same here, we can write this as, sorry, my bad, this is I times Q, and this is P minus I times Q equals to 0. Now if you look at this equation, this is a standard homogeneous system of linear equation in which Ax equals to 0. So what you have to do simply is to find a non-trivial solution to P minus I, okay, or non-trivial solution. So in the case we say that if P is defined by that, it means P minus I can write this as nothing but equals to 0.6, 0.4, 0.3, 0.7, and U minus identity matrix, which is 1, 0, 0, and 1, right? So if I subtract this P minus I here, I will have this thing here as P minus I, which I know from now on will say A, right, is equals to, it will be nothing but minus 0.4, 0.3 will remain the same, 0.4 will remain the same, and this will come out as 0.3. Now we can think of now this as nothing but an finding solution for x equals 0, so I can augment it this way as 0.4, 0.4, 0.3 and 0.3, and now I augment with 0 for the sake here. So if I add the first row with the second row, so what you will have here is minus 0.4, 0.3, 0 and 0. You will still come out at 0 and 0. Okay, now it's a 2 by 2 system, and the last row is 0. It means the solution is actually consistent. The thing here is we have got one free variable, right? So we know that when we have a one free variable, so I can write one dependent variable in terms of that free variable, which is nothing but equals to minus 0.4 times x1 plus 0.3 times x2 equals to 0. In this case, x1 will become 3 times 4 x2, right? So if I want to write the solution as x1 x2, this will be nothing but equals to 3 by 4 x2 and x2 here, so it comes out to be 3 by 4 and 1 x2, right? So we know that this is nothing but a vector which is 3 by 4 and 1, 3 by 4 and 1. So this is the solution to that equation, right? Now not solution exactly, but yeah, but this is actually the basis for basis vector for that space defined by actually p minus I, right? So you can choose any multiple of x2 to generate this solution vector x1 and x2. So if I could choose x2 is equals to 4, so this I will have a solution as 3 and 4. Now this 3 and 4 is nothing but x1 and x2. And what is x1 and x2? x1 and x2 is nothing but equals to ax equals solution to the equation ax is equal to 0, and a in this case is p minus I times x, and now x is the solution to that equation, which is nothing but a, if you start from here, is nothing but a steady state vector. So x is a steady state vector, which is x1 x2, 3 and 4 is a steady state vector. So any multiple of x2 when multiplied with when x2 is multiplied with any value of x2, which is multiplied with this vector, when you put it in the system and pass multiple iterations through p, eventually that vector will remain the same after a certain amount of iterations, and this is a vector called a steady state vector. Now you can you can check it by simply multiplying this thing. I think you can take it as your simple assignment. You can take any of the vector here and start with any vector, any value of x1 and x2, but you will see that you will converge to any multiple of these vectors. Now, so if P is a probability transition matrix, is an n by n, of course that will be a square matrix. In this case, this is a stochastic matrix because that defines the probabilities. It is written in terms of probabilities. Then P has a unique steady state vector Q. So if you start with x naught as an initial state, in which xk plus 1 is equals to p times x of k, then the Markov chain defined by this matrix P, as I showed you the graphical representation of that thing here, so actually converges to Q as k the number of iterations over which you perform those multiplication actually approach infinity. right? So you can do a lot of examples given in this section to work out the steady state vector. So I mean, you can actually look at those examples. Say, let's say 0.6, 0.2, 0.4, and 0.8, right? Now this is a probability transition vector. So you have to check if this matrix is a steady state matrix, right? So what you do is simply, if it is a steady state matrix, it means PQ is equal to Q, and we know that we have just found out this is nothing but P minus I times Q equals to 0. So what we have to do is to find the solution to this homogeneous system of equation, which is you can write this as in the matrix format. If you multiply that, minus 0.4 comes out 0.2, 0.4, and this comes out minus 0.2, right? Now if you do those calculations, right, what you will have here is simply Q, or you can find that, and you can find that if Q is really coming like that, or what you can do is simply multiply this P of Q with Q. So in this case, 0.6 times 0.2, 0.4 times 0.8 into 0.3 times 0.7, which gives the value of 0.6 times 0.18 plus 0.14, which is 0.32, 0.4, 0.12 plus 0.056 comes out to 0.56, which will be 0.68, right? So the answer is 0.32 and 0.68. So this is Q, but this is not equals to Q, right? So it means Q is not a steady state factor for this equation. Okay, so that's end the discussion on Markov chains. In the next lecture we will talk about eigenvalues and eigenvectors. It is a very important topic, one of the most important topics in linear algebra, because it helps you really understand the significance of linear algebra when applied to practical engineering problems. So hopefully you have understood the lecture, and Allah Hafiz.